So we are finishing up chapter 9 today with this new idea called antiderivatives. So we've been spending the last few months of the semester talking about derivatives, and now the idea is we want to go backwards. So just like when you learn like addition, later in life you learn subtraction to kind of undo all that addition operation that you learned, so that inverse operation idea. So now we're going to think about an idea of an antiderivative. So in other words, instead of taking the derivative of a function, what if we want to go backwards and take the antiderivative? So we're going to undo what we would have done if we were taking the derivative. So we get this definition about a function is called an antiderivative of f on an interval I if we can take the derivative of that capital F and it's equal to that lowercase f for all x in our interval. So that's the idea, is we're going to go backwards. Instead of taking the derivative like we've been taking, we're going to start with the function and ask, what did we take the derivative of to get to this function? And the example that I'm starting with here is, let's say we have x squared. And the question is, what did I take the derivative of to get to x squared? So I want you to think about that for a minute. Pause the video if you need to, but definitely see if you can come up with at least one answer to this question. What's something you would have taken the derivative of to get to x squared? So hopefully you're thinking, okay, to take a derivative, normally I subtract 1 from my exponent. So I would have had to have taken the derivative of hopefully something of the form x cubed. So hopefully you have that much so far. And if that was the answer, you're like, maybe it's just x cubed. Well, if you try and check your work, right, if you take the derivative of x cubed, you're going to get 3x squared. And there's no 3 here, right? So how would I get rid of the 3? I don't want to put another 3 here, right? Because then I would take the 3 down and I would get 9, and that's the opposite of what I want to do. So I want to kind of undo that multiplication that I get from 3. And the opposite of multiplication, right, is division. So instead of multiplying by 3, I'll multiply by 1/3 or divide by 3. So here's an example, right, of an antiderivative of x squared. If I take the derivative of this, I will get x squared. Now, some of you may have come up with something else because there's something really interesting about antiderivatives. This is certainly an antiderivative. We checked that. We can take the derivative. We'll get x squared. That'll be great. But maybe some of you thought about another function. 1/3 x cubed, still great. But you could also say maybe plus 1, right? That, if we take the derivative of that, we're still going to get an x squared here as we take the derivative. But then the derivative of 1, remember, is 0. So the derivative of this is still x squared. So when we take the derivative, of this function, we still get x squared, even though that we've tacked on this plus 1. So keeping that in mind, right, you could have a whole family of functions, 1/3 minus 7, or 1/3 x cubed plus pi. Any of these answers are all antiderivatives of x squared. So when we take a derivative, we get one function, right? There is one derivative for each function. But when we go backwards and take the antiderivative, we actually end up with a whole family of functions. And that's actually what our theorem is going to say. That's our sort of first theorem about antiderivatives. So the theorem's the following. So we get that if f is an antiderivative of lowercase f on an interval I, then the most general antiderivative of f on I is f of x plus c for some arbitrary constant c. So in other words, when we talk about notation here, we're going to be using something known as the indefinite integral. And we'll learn a lot more about integrals in the next chapter, but this is sort of the first time you're going to see this notation. So we're going to say something like we're going to integrate lowercase f of x with respect to x, that's what this dx means, and we will get that antiderivative f of x plus c. So this is like the notation, like when we take derivatives, we have that prime notation or the ddx. The notation to take the antiderivative is this little symbol here with telling you what you're taking the antiderivative with respect to. So this is the notation for antiderivative. You have to have these two things, both the integral sign and like a dx that tells the reader what you're integrating or what you're taking the antiderivative with respect to. So I have a whole bunch of examples that we're going to look at of things that we already know the antiderivative for because we know the derivative so easily. So I have a nice little chart that we're going to fill out, and then we'll try a few examples here in the video, and then we'll do a few more in class as well. Okay, so here's a table of a few functions that we're going to be able to write down the antiderivative for pretty easily because these are things that are going to be pretty common and that we can actually just think about what would I have taken the derivative of to get to this, right? So we're just going backwards. So first we'll start to x to the n. So when we take derivatives, remember we subtract 1 from our exponent and we bring down our exponent and multiply it in the front. So here when we're doing antiderivatives, we'll do the exact opposite of that. We'll add 1 to our exponent. Right, that'll be going backwards, and then instead of multiplying by the old exponent, we'll divide by that new exponent. So you'll get this 1 over n plus 1 out front. And remember, all of these antiderivatives are going to have this plus c tacked on to the end, because remember, you can add any constant, because when you take the derivative and go backwards or forwards, that constant will go to 0. So we're good to go by tacking on these plus c's to any of these. You'll notice in this works for anything but not when n is equal to -1, right? Because you get a 0 in this denominator, which that would not be an ideal situation. So here, now we're looking at 1 over x, and if we take the antiderivative of that, we're going to get ln, right? If we take the derivative of ln of x, we'll get 1 over x. In this situation, we go ahead and put absolute value signs around the x because we don't know that x could be negative in this situation, and we wouldn't want to plug in negative values for the natural log. So the antiderivative does have some absolute value signs around the x, which normally it wouldn't have, right, when we were taking its derivative of that, but that's what kind of saves us going backwards. Now e to the x. So what did we take the derivative of to get e to the x? Hopefully we remember that that is e to the x. That's the antiderivative of e to the x because the derivative of e to the x is e to the x, and the antiderivative of e to the x is e to the x. Now we have cosine of x. So the question is, what did we take the derivative of to get to cosine of x? And I believe that that one is sine of x. I often have to think about these because I don't want to go backwards. But the antiderivative is sine because if I take the derivative of sine of x, I'll get cosine of x. Similarly for sine of x, I think that would not be, it would be cosine of x plus c. But remember, the derivative of cosine is negative sine, so I think this is going to need a negative in front of it. It's the antiderivative of sine. Secant squared of x is a function, so the question is, what's the antiderivative of that? So if we're going backwards, so what did we take the derivative of to get secant squared? Hopefully you remember that that's tangent of x. I've got two more here. Secant x, tangent x. So the question is, what did I take the derivative of to get secant x, tangent x? Hopefully you remember that to be secant of x. Next down here I have 1 over the square root of 1 minus x squared. So thinking about that, what did I take the derivative of to get to that? Hopefully you remember that that's the derivative of sine inverse of x. So that's the antiderivative of 1 over 1 minus x squared. You might also say it's negative cosine inverse of x. That's fine as well. But this is generally the more standard way that we think about that antiderivative. It's a little bit easier. More derivative that we want to look at, and that is if our function, so if f of x is 1 over 1 plus x squared, it just didn't fit on the previous slide, then if we find capital F of x of that, remember this is the antiderivative for tan inverse, right? If we take the derivative of tan inverse of x, we would get 1 over 1 plus x squared. So that kind of helps us fill out our chart. And I want to kind of work 3 basic examples for us to get a sense of how to find these antiderivatives. And then in class we'll do some more complicated examples and do some class exercises to make sure we understand the concept of the antiderivative. So first of all, we'll look at g of x, which is a 4 sine of x, and then plus 2x to the 5th minus the square root of x over x. And we want to find the antiderivative. That's going to be the instructions. So when I first look at this, it looks like this one right here is good to go. I can use my rules from that previous chart to find the antiderivative of that very easily. But I do not have an antiderivative rule about fractions, so I'm going to have to split that up first before I can even take the antiderivative. So if we look at g of x, we can say that that's 4 sine of x. And then let's split this fraction into two fractions, right, here and here. So that's 2x to the 5th over x, and then minus the square root of x over x. And so if we simplify that before we even take the antiderivative, we'll get 2x to the 4th, and then minus, if we look at this, I think that ends up as being 1 over the square root of x. Right, x to the 1/2 divided by x to the 1 will leave us an x to the negative 1/2, or 1 over the square root of x. So now we're ready. Maybe we'll even write this a little bit more easy for us to recognize. We'll take the exponent here and rewrite it as a negative exponent. And now we want to find the antiderivative of this function. So we're going backwards, right? From instead of taking the derivative, we're going to do everything backwards. So we're going to have to go to the next page. So put this over here, 4 sine of x plus 2x to the 4th minus x to the negative 1/2. So that was our g. So now we're going to find capital G, or the antiderivative. So we have to think about, what did they take the derivative of to get sine of x? And I believe that's negative cosine, right? Because the derivative of regular cosine is positive. The derivative of cosine is negative sine. So we need the negative here, and the 4 just stays out front, just as it does when you take the derivative. Then we have 2x to the 4th. So remember, for exponential function, for power functions, you're going to add 1 to the exponent. So the 4 becomes 5. So instead of subtracting, we're going to add. And instead of multiplying, we're going to divide by that new exponent. So this piece right here and this, that's the antiderivative of that power function. And then similarly for the x to the negative 1/2, we're going to raise that to the positive 1/2, right? Thinking about the fact that negative 1/2, adding 1 to that, right, gives us positive 1/2. And then we divide by our new exponent, 1 over 1/2. And then don't forget to tack on that plus c at the end of your antiderivative. So I'm going to go ahead and simplify this out a little bit. 1 over 1/2 is just 2, so in case you needed that extra step. So here's our antiderivative for g of x. Don't forget to add on the plus c, because we can definitely have many different antiderivatives for just one function. So you could add 3, you could add 4, you could add nothing, and all of those things will have the same derivative once you take it of the new function, if we were going forwards instead of backwards. Okay, have a couple more examples just to see if we can play with some things and see if we can start thinking about how these antiderivatives work. I have an f of x equal to cosine of 3x. So if we look at this one, thinking about if we were going to take the derivative of this, right, we would need to use a sort of chain rule on this 3x part. And so we're going to try to think about doing the chain rule backwards. So if we were integrating this backwards, the antiderivative of cosine would be sine of 3x. You don't ever want to change that inside function. So it was cosine of 3x. Now we have sine of 3x. If we were taking the derivative, remember for the chain rule, we would multiply by 3. So thinking about doing everything backwards, instead of multiplying by 3, in this case, we'll divide by 3, or you can think of it as multiplying by 1/3. So that's the going backwards for taking the antiderivative. And then don't forget, you want a plus c here. So this one is a little bit more complicated than the first ones because it's not straight from one of the rules that we have. It's thinking about the chain rule and how the chain rule works with antiderivatives. So just think about the fact that we want to undo cosine. Going backwards, we're going to say that that's sine. It's a chain rule. So just like the chain rule, we're going to leave the inside function alone. And then we want to think about doing the opposite of what we would do with the chain rule. We would multiply by 3, but here we'll go ahead and divide by 3. And we can only really do that because of the fact that this is just a constant here. If this had been 3x squared, that would have made this a lot harder. But because it's just a nice linear function on the inside, we can just multiply by the reciprocal of that constant, and everything works out fine. One final example, we have h of x. Let's look at this one. H of x is x e to the x squared. So we're trying to think about, what did I take the derivative of to get to this? So that's the question. So what did I take the derivative of to get to x e to the x squared? So hopefully you recognize you usually, a derivative of like an e to the x sort of function, remember an exponential function is always comes from, right, the original function itself. So if we were going to take the derivative of just e to the x squared, think about that. The derivative of that would be e to the x squared, so we would definitely have this piece. But then we would have times the derivative of the exponent, and the derivative of the exponent would be 2x, right? So out front here you should have a 2x if we were just taking the derivative of this. So it's off by a factor of 2 right now in terms of if we were to take the derivative of this h. So I'm going to go ahead and put here in front the opposite of what I needed, right? So here I needed 2x, but I don't want the 2. I want the 2 to go away, so I'm going to put a half out front. So that's kind of going backwards and thinking about what happens. And then don't forget your plus c. And then you can always check this work if you didn't believe what I just did there. So if we take this derivative, we have 1/2 e to the x squared times the derivative of the top is 2x, right, plus c. And that is in fact, or I guess the derivative of c would be 0. So we cancel some stuff out, we get exactly e to the x squared, which is exactly equal to h of x. So you can always check your work on these, and the idea of these antiderivatives, these are kind of the harder ones. I'm not going to have things that much harder in this section. This is really trying to undo a chain rule situation, which we'll learn a little bit more about later in chapter 5. The big idea is to really ask yourself, what did I take the derivative of to get to this thing? And most times what you're doing is trying to kind of do the opposite of what you would have done if you were taking the derivative.